Hey everybody, this is 7b on torque. So they say a long rod of length L and negligible mass, so we don't have to worry about the mass of the rod, supports a box of mass M. The left end of the rod is held in place by a frictionless pin about which it can freely rotate. So that's our pivot point, the pin. In each case, a vertical force is holding the rods and the weights at rest. The rods are marked at half-meter intervals. So there's a half a meter, so that's 1 meter, 2 meters, 1.5 and 2 meters there. So although I find it helps in this case, on a lot of these, it's just ratio. So I just call this a unit of 1, a unit of 2, 3, and 4 there. And so there's just the picture, the setup here, where we're moving the hand that's holding the rod at different places, and we're moving the box to different places there. So I'm actually going to draw the pictures on the next slide here. It says, with the instructions, it says, rank the magnitude of the vertical force F applied to the rods to keep them horizontal here. So how are we going to do this? So here's the thing. It's not rotating, so we need to think about the torques here. So this thing, I'll just say it has a mass of 1. And on this one, on A, I'll just call that a unit of 1. So remember that torque is force, that's its weight, which we're saying is 1, times its lever arm, and that's a lever arm 1. So this thing is creating a torque of 1. So in each of these cases here, I'm going to write the forces up here, the lever arms here, and the torques down there. So what does the hand have to do? Well, to keep it from rotating, it must balance the torque of the mass there. So it must also have a torque of 1, just in the counterclockwise direction. We can see here its lever arm is 4 units. So what times 4 gives you 1? 1/4 the force. So if this thing has a weight of 1 Newton, then you would only have to push up with 1/4 of a Newton to hold it in place there from rotating. So let's keep that up here again with force and lever arm and torque like this. This thing again has a force of 1. Here we can see it has a lever arm of 4. So if we multiply those two together, it has a torque of 4. So for the hand to keep it from rotating, it must also have a torque of 4. But we can see that the hand's lever arm is 2. So what times 2 gives you 4? 2. So if the box weighs, let's say, 1 Newton, then you would actually have to push up harder than that. You would have to push up 2 newtons. So this would make the box feel heavier in a sense. Okay, let's do this one. Same format here. The box is a weight of 1. It's at a distance of 3, so its torque is 3. So the hand has to create a torque of 3 to keep it there. But its distance is 4. So what times 4 gives you 3? 3/4. So you would push up with 3/4 the weight of that box, and it would keep it there. All right, here we have a weight of 1, a distance of 2, so a torque of 2. The hand has to create a torque of 2 then. It's got a distance of 4, so what times 4 gives you 2.5. Then over here, the box has a weight of 1, a lever arm of 1, so a torque of 1. The hand would also have to create a torque of 1 the other way to keep it there. It's got a lever arm of 3, and so the force must be 1/3, so 1/3 the weight of the box. And then finally over here, the box has a weight of 1. It is 2 units out, so that's its lever arm. So 1 times 2 is 2 units of torque. That means the hand must create 2 units of torque to keep it there. But what times, it's got a lever arm of 1, so what times 1 gives you 2? 2. So once again, just like this one, you'd actually have to press up with twice the force of the box there. So now we can rank them. We can see here that both F and B, they're equal to each other. So greatest force would be F, which is equal to B. You'd have to push with twice the weight of the box. Then it's actually C up here with 3/4 of the weight of the box. And then we go to D here with half the weight of the box, and then E with 1/3 of the weight of the box, and then finally A is the least with only 1/4 of the weight of the box there. All right, I'm going to get a new set of drawings because on this one, they say, on the diagrams above, sketch the forces acting on these objects. So again, let's say this has a weight of 1. The system is the box and the rod, they say. So here we have a force of F down on here. The hand is an external force to the system. By the way, this is gravity, so this is the force of gravity on that box. The rod itself, they say, is nearly massless, so we don't have to worry about the force of gravity on it. Remember that we saw from the previous one that we just did that this would be about a quarter of that force. So I'll call this one 1/4 F. But look, here is a problem. If it's being pulled down with a force F here and being pushed up with 1/4 F here, why isn't it moving down? Why is it the downward force beating the upward force here? They balanced when it was torques, when we had to include their lever arms, but they're not balancing now. There must be something else, and it would be the pin right here. So the pin actually is pushing up on the rod too, with 3/4 F. How do I know it's 3/4 F? Because 3/4 plus 1/4 would be equal to the force down there. So now, again, on this one, we would have a force F down. In this case, we said that the hand was pushing with 2F up. So why isn't the upward force winning? 2F up, F down on the system, it must be the pin again. But in this case, the pin must be pulling down with a force F. So we can continue that on each of these. The box with force F, the hand, in this case, if you remember from our previous drawing, was pushing up with 3/4 of F. So again, the pin must be helping us out. Down's winning, we got to balance it out. The pin must be pushing up with 1/4 F to make everything balance. Let's go through these last ones real quick. So the box down with force F. In this case, the hand was pushing up with 1/2 F. So you can see here again, the pin's got to come to the rescue and give us an additional 1/2 F up in that case there. And then here, the box down with force F, the hand up here with 1/3 of F, we said. And so the pin must be pushing up with 2/3 of F. And then finally on this last one here, the box is being pulled down with F. Here we said the hand was pushing up with 2F. So in this case, the pin must actually help keep the rod from moving up. The pin must be pulling down with a force of F there. So that handles the drawings that they want for part B. And it also gets to part C here. In which cases is the force from the pin up, down, 0? Justify your answers. Well, we've basically done it here. So it is up on the force of the pin in cases A, C, D, and E. Because in each of those cases, the force up by the hand is not enough to balance out the force down on the box there. And then the pin is down in cases B and F. Because in each of those cases, the force down by gravity on the box is less than the force up from your hand. In no cases was it 0. The box would have to be sitting right on top of the hand to make it 0 in that case. All right, one last quick thing here. It says, explain in a short paragraph with a reference to the picture above why it is easier to hang a shopping bag from the crook of your elbow, like in this picture, see how happy he is, than to carry it suspended from your hand at a 90-degree angle. Oh, she's not happy. She's not thinking about torque because she has a big lever arm here. So even if the bag weighs the same, you will get force times lever arm, a bigger torque there, and that torque will want to rotate her arm, which she is trying to fight. But this guy right here, he's got a little teeny tiny lever arm, so even with the same force, he will have a smaller torque compared to this person's much bigger torque.